Kia ora and welcome to question 1 of the 2023 Schol Calc exam. This question here, we've got part A, a conics problem, and the algebra of this can blow up if you don't see the shortcuts. Part B is a system of equations involving logs, and part C, another conics question involving a proof. We're going to look at 2 ways of doing part B and part C in this video, although I'm sure there are other ways. As always, make sure that you've tried the problems before we go through them. Although I imagine some of you are probably watching this video to see whether you got them right in the exam. So, the first one, we need to find the equation of the line QR, and to do that we need to find the points Q and R. We're given the point P. A couple of other things to note. We can find the radius of the circle by using that point P, and the hyperbola xy equals k. K must be a negative number because it's drawn there in the second quadrant. The second quadrant is where x is negative and y is positive. Those two numbers multiplied together would give a negative value for k. We don't need simultaneous equations to solve and find the point Q. We just use symmetry. Okay, there's an axis of symmetry that comes through here. It's the y equals negative x line. And based on a little bit of geometry there, we can see that P and Q are equidistant from that line. So if P is the coordinate negative 8, 6, then Q must be the coordinates negative 6, 8. We'll look at the algebra of how you can get negative 6, 8, but that's a quick way of doing it. Now, to find the radius of the circle, we just go from the origin out to the point P, and by constructing that right angle triangle, we're going 8 across in the x direction and 6 up in the y direction, and if you do Pythagoras on that, you get a hypotenuse there of 10. So the radius of the circle is 10. And therefore the r coordinate is 10, 0. Okay, and to answer the question, lastly we need a straight line. The gradients can be found by using rise over run between the point Q and R. So if Q is equal to negative 6, 8 by symmetry, then the gradient using rise over run, draw a line between Q and R there. From Q to R we go across 16 in the x direction and we go down 8 in the y direction. Helps if I get the gradient around the right way. Negative 8 over 16, which simplifies to minus a half. And we can use any of the points. I'll just use the point Q. QR is y minus 8 equals negative 1/2 x plus 6. We can rearrange that to be y equals 5 minus 1/2 x, or mx plus c form. Now, if you didn't notice the symmetry for finding the coordinates of Q, you could do the following. Let's just change colors. You could go xy equals k. We could plug in the point P. The point P was negative 8 and 6, so that gives you the k value of negative 48. Then we've got a hyperbola, y equals negative 48 over x. We can sub that into the circle equation. Remember that the circle has a radius of 10. So we've got x squared plus y squared equals 100. If we sub that into there to solve a simultaneous equation, we've got x squared plus negative 48 over x all squared equals 100. That's a disguised quadratic equation. We can times the whole thing through by x squared. We're going to get x to the 4 minus 100x squared, okay, because I times the right hand side by x squared and then move it to the left, and plus 48 squared equals 0. You can solve that by completing the square, or you could solve it using the quadratic formula. and you come out with x squared is equal to 36, or x squared is equal to 64. They're your two possibilities. Now we know that x is a negative number, so x equals negative 6 from the first one is the only relevant one, and x is equal to negative 8 is the other one. Now we already got told that x was negative 8 for the point P, which means that the Q value we want is negative 6. And then find the Y value by subbing back in to the hyperbola equation. Negative 48 divided by negative 6 is equal to 8. So we can do that algebraically, but it's really, really short if you just use the symmetry. And you need the symmetry argument for the second question. So if we look at what the second question is telling us, prove that the line RT is parallel to the line PQ no matter where the hyperbola intersects the circle. There's a slight mistake, I think, in this question, because if we just get rid of all that, we're told that x is a negative number, so therefore the hyperbola needs to be drawn in the second or the third quadrant. Yes, it's currently drawn in the second quadrant, but what's stopping the hyperbola being down here? And if a hyperbola is drawn down there, it would also be up there, but we've just restricted it. And that would be a k value that's positive. Okay, it just told us that P in the first part was negative 8.6, but what happens if P was, say, this point? Then we'd have a bit of an issue, because Q would be here, and that line there is clearly not parallel to RT. So there's a slight mistake, I guess, in the wording of the question, but the intention, I guess, was to say PQ, let's find the slope of PQ, and let's look at the slope of RT. Now, RT is trivial, the slope is 1. We just need to give an argument as to why PQ has a slope of 1. It's saying no matter where the hyperbola intersects, so we can't use the coordinate P as negative 8.6 anymore. But what we can do is say, hey, what about a P value of, say, AB? Okay, this is generalizing. If the coordinate P is AB, then Q, all we need to do is look at kind of a specific example. When our x value was negative 8, the y value became positive 8 for the q value. So it's going to be negative b, negative a. Okay, that's our coordinate for q. Whatever the b value is for p, in the first case it was 6, well, the x value is going to be negative 6. And same for the y value switched around. Now, if we find the gradient between those 2 points, slope of PQ, rise over run, so take the rise is negative A minus B, and the run is negative B minus A, and we can see that that comes to 1. And then the slope of RT, well, technically we don't have a radius of 10 anymore because the point is changing. The point P defines the radius. But we could just say, okay, the radius is r, and therefore the point T is at negative r, and the slope for that will be rise over run, so it goes out r, up r, so r over r, which also equals 1, and that's our proof. Okay, we don't need anything more than that because we've argued that there is symmetry. You could be maybe a little bit more defined around the symmetry and say it's the line y equals minus x, as I discussed. Okay, part B, solve the system of equations. We have to be careful with the use of log rules here. So our first equation, 4 log base 2 of 8x cubed plus log base 5 of y to the 6 equals 17. And our second equation was log base 2 of x to the 5 plus log base 5 of y squared equals 3. Now, these equations have quite a bit of similarity to them, and what we can do is make them even more similar and then apply a substitution. The first thing to realize is that 8x cubed can be written as 2x all cubed. Okay, and by doing that, by switching the 8x cubed out, we can now bring the 3 down the front with the 4. We couldn't do it before because 8x cubed, you can't just move the 3. You have to write it as 2x all cubed. So that first equation is going to become 12 log base 2 of 2x. We can do the same thing with the next term. We can bring the 6 down the front. So we've got 6 log base 5 of y, and that equals 17. Second equation, third term, 5 log base 2 of x, and 2 log base 5 of y is equal to 3. Now you can see we've got the similarity, so we're able to make a substitution on that term, but the top left term, 12 log base 2 of 2x, needs a little bit more tidying up. So what I'm going to do with that one, just change colours so that we can make it a little bit clearer. This one here, I'm going to write log base 2 of 2x as log base 2 of 2 plus log base 2 of x. Because when you add logs together, you multiply the arguments. And log base 2 of 2 is just equal to 1. Okay, bear in mind that both those things then need to be times by 12. Okay, so our equation simplifies further. We've got 12 plus 12 log base 2 of x. Now I'm going to move that 12 to the other side by taking it off the 17. So we end up with 12 log base 2 of 2, not 2x, sorry, just log base 2 of x, plus 6 log base 5 of y equals 5. And the same second equation, I don't need to change it anymore. Okay, now we're going to make our substitution so that we can solve a linear system of equations. Wherever there's a log base 2 of x, I'm just going to call it u. So I've got 12u plus 6, we'll do v for the green stuff, and 5u, terrible plus symbol, plus 2v equals 3. If we solve that simultaneous equation using any means that you know how, calculator's fine, you're going to get u equals to 4/3 and v is equal to negative 11/6. Now bear in mind that u was equal to log base 2 of x, and therefore to get the x value we need to take 2 to the power, so 2 to the power of 4/3, and our y value comes from solving log base 5 of y equals negative 11/6, and then y is equal to 5 to the power of negative 11/6. One small little observation. If we go back to the original problem, the y values here are both powered by an even number, which means the plus and the minus solution for y both work. And so we actually need to stick a plus or minus on that. It doesn't look like it would work for our substitution, but our substitution came from some log simplifications. And so we actually lost that solution in the process of simplifying. The reason I knew that that was a solution is I actually graphed both the original equations on Desmos and found that there were answers I was missing. In the graph, there were points of intersection that were extra, and I tried to work out what had happened, and I realized the even powers. Okay, so that's one way of doing the problem, but as I said in the outset of the video, we'll look at another way of doing it. The other way is actually just to substitute. Like we used a simultaneous equation method there where we could make a substitution, but we can sub one equation into the other, and it falls out fairly nicely as well. So let's just have a look at that. Okay, if I take, we'll start off with the first equations again. 4 log base 2 of 8x cubed plus log 5 of y to the 6 equals 17, and log base 2 of x to the 5 plus log base 5 of y squared equals to 3. Now, from the first equation, let's call these equation 1 and 2, like I didn't do that before, but it's quite useful. I can write, what can I do? I can split this 6 here. I can split it into 2 times 3 and then move a 3 down the front. Okay, and by doing that, I'm going to end up with log base 5 of y squared. Think about why I'm doing that. Is equal to 17 minus 4 log base 2 of 8x cubed, all divided by 3. So I split that 6 into 2 times 3, I leave the 2 at the top, bring the 3 down the bottom, rearrange that equation and make log base 5 of y squared the subject. And I'm doing that because I can do the same thing with equation 2. Log base 5 of y squared, it's a bit more obvious in equation 2, is just 3 minus log base 2 of x to the 5. Okay, so those equations there both have the same subject, and now I can equate them and I've eliminated the y's. So equating them, 3 minus log base 2 of x to the 5 is equal to 17 minus 4 log base 2 of 8x cubed, all divided by 3. Okay, I'm going to times both sides by 3, and then I'm going to rearrange the equation. So timesing by 3 first, I've got a 9, then the 17 that's on the right is going to go to the left, so it's going to be minus 17. And that's going to equal, the 3 on the left-hand side when I times, it's going to give minus 3 log base 2 of x to the 5. Then I'm going to put that on the right-hand side, so it's going to be positive 3 log base 2 of x to the 5 minus 4 log base 2 of 8x cubed. So I'm trying to solve for x, and I want everything that's got x's in it on one side of the equation. Now the last thing is I can't subtract these logs until I've dealt with the numbers that are in front. So the 3 and the minus 4 are in the way, and I can't subtract them yet. So what I'm going to do is write log base 2 of x to the 15. I'm going to take the 3 back up the top, x to the 5 all cubed, and then the 4, I don't really worry about the minus as such, but I can move the 4 up the top, log base 2 of 8x cubed all to the 4. And lastly, that equals negative 8. I'm going to use log rules for subtraction. Log base 2 of x to the 15 over 8 to the 4 x to the 12. Okay, last bit of simplification. 8 to the 4, without reaching for a calculator, 8 is 2 cubed. So that's actually 2 cubed to the power of 4, or 2 to the 12. And the x's simplify. So we've got log base 2 of x cubed over 2 to the 12. I'm going to take 2 to the power on both sides to get rid of the log. 2 to the power of negative 8 is equal to x cubed over 2 to the 12. And then times both sides by 2 to the 12. X cubed is equal to 2 to the 12 times 2 to the minus 8, which of course is 2 to the 4. Cube root, x is equal to the cube root of 2 to the 4, which is the cube root of 16, or 2 to the power of 4/3, which is what we got before. Now the beauty of this method is that when I go back to find the y values, all I need to do is sub in 2 to the 4/3 back into one of the original equations. And when I rearrange that equation, because there's a y squared there, actually I'd probably be best to use the next one. Use this one here, it's a bit tidier. When I rearrange it, I'm going to get y is equal to plus or minus the square root of whatever's on the right-hand side, and I'd get all of the answers without having to look back at the original equations. Okay, our last question for this section, this video, we've got a conics proof involving a parabola. Now, I actually prefer my second method for this, but it wasn't my original method. So I'm going to show you what I originally did, and then I'm going to show you a much quicker way of doing things. So the key things to realize here is we've got two lines that are perpendicular, and they intersect the parabola at 2 points A and B. We know how the slopes of OA and OB relate because they're perpendicular lines. And then we need to find the coordinates of A and B, find the line between A and B, kind of like we did for the very first part of this question, and then find the x-intercept of that line. So that was my thinking. So first up, let's just call this coordinate here A. We'll go with A is the x value and the square root of Ka as the y value. Because if we substitute x is equal to A into the parabola equation and we take the square root, we want the positive square root because A is above the x-axis. B, on the other hand, is different because when we take the coordinates of B, which I'm just going to call the x value B, I'm very original there, I'm going to take the negative square root of KB, okay, because I want it to be a coordinate that's below the x-axis. The slope of OA is equal to rise over run. It's pretty easy when it's coming from the origin. It's just the y value, root Ka, divided by the x value. The slope of OB, be careful with this. The run is B, goes across B. The rise is negative square root xb because we need to have a negative gradient. It's a line that's going downwards. And then lastly, we know that these gradients here are negative reciprocals of each other, or they multiply to -1. So MOA multiplied by MOB, which is equal to root Ka over A multiplied by minus root Kb over B is going to equal -1. We can get rid of the minuses on both sides. We can multiply those surds together. When we do that, we're going to get K times root AB over AB is equal to 1. And then lastly, if I square both sides and rearrange it, I come out with K squared is equal to AB. So that's a special relationship here that tells us that if these coordinates are such that the lines from the origin to those coordinates are perpendicular lines, then the x values, A and B, the x values of the points will multiply to equal K squared, where K is from the parabola equation. Okay, so that's actually a really crucial bit of working out for this particular problem. I'm not going to rewrite it other than to say K squared is equal to AB. You'd obviously need to show your working in the exam. If you're watching this preparing for future scholarship exams, I've just written all over a diagram. You get to keep the exam paper after. So it pays to redraw out your diagrams in your book to explain what your variables are. Now, we want the equation of the line AB, because if we find that equation, we can find its x-intercept. I'm just going to use the point A. Okay, goes through the point A, which had the coordinates A and root Ka, and I want to work out the slope, which is rise over run. So I've got y minus root Ka is equal to, what's rise over run in this case? The rise, so setting up a right angled triangle, colour it in yellow so we can see it. The rise is root Ka plus root Kb. Be careful there, it's usually y1 minus y2, but the y2 is negative. And then the run is A minus B. So we've got a slope of root Ka plus root Kb all over A minus B multiplied by x minus A. That's the slope-intercept form of a line again. You could use y equals mx plus c if you wanted as well. Now we're going to set y is equal to 0 to find the x-intercept, which we don't know is k, we're trying to prove that. And then we're going to do some rearrangement, so minus root Ka all multiplied by A minus B. I'm going to move that fraction, we'll get rid of that fraction by moving the denominator upwards, is equal to root Ka plus root Kb all multiplied by x minus A. And I'm going to solve this for x. So I'm going to do division on that factor in the front, and then I'm going to add A. So x is equal to the left-hand side stuff, all divided by that factor in the front. Oopsies, my surd needs to go over the a, plus a. We can do a little bit of tidying up. The first thing we can note is that we can divide through by root k on top and bottom. And just be careful because the a is still under the surd in the front. So we've got minus root a all times a minus b over root a plus root b. And then I want to add a to this, so I'm going to put it over a common denominator by timesing that by root a plus root b, top and bottom. Okay, now I can add those terms. Notice that the minus root a times a, which is in the front here, is going to cancel with that one when I add. So we're going to get root ab plus a root b, bit of symmetry there, all divided by root a plus root b. I'm now going to times by conjugates, root a minus root b. I'm trying to make this equal to k, and it's a bit of a concern that I have no k's at all because I got rid of them, but I'm going to use that relationship we proved. Okay, so tidying that up, be careful that we're actually multiplying double brackets at the top. So we get root ab times root a, which is ab, a times root ba, so a root ab, minus root ab times root b, so minus b root ab, and then lastly minus ab. So those terms cancel, all divided by a difference of two squares of a minus b. And lastly, we get a little bit of factorization here because both of those terms have a common factor of root ab. So we've got root ab multiplied by a minus b, all divided by a minus b, cancel, cancel, square root ab apparently is the x-intercept. Interestingly, it's the square root of the x values of the points a and b. But remember that our relationship k squared equals ab comes in, the square root of that is k. And we know that k is a positive number because of the picture. So that equals k, and we're done. Not too bad, but definitely the hardest problem in this section. Now, I said that there was a different way of doing it, so let's change colour pen and just have a look at that. Okay, what you can do, let's just redraw this parabola. Not too bad. We can consider just any old straight line here. We don't know it goes through the point K, we've got to prove that, but let's give this equation y equals mx plus c. And let's consider the points of intersection, which are points A and point B. How do we find the points of intersection? Well, we just solve a simultaneous equation. So we've got y squared equals kx, and we substitute the line equation into it. So we're going to get mx plus c all squared equals kx. If we expand and then rearrange, we're going to get a quadratic equation, m squared x squared plus 2mc minus k all times x, and a c squared constant. And look, we don't actually need the roots. That's the cool thing about this method. What you need to realize is that the product of the roots helps us. This is a bit of a shortcut because we've actually already done this problem. But what we found earlier was that the x value of a, which was a, and the x value of b, which was b, we found that a times b was equal to k squared. So this method still needs that relationship. And that's because you need to factor in the perpendicular lines somehow. And if you do, that's what you find. So the cool thing about this is that relationship is related to the product of two roots. And the roots a and b, the x values a and b, correspond to the roots of this quadratic equation that we've got. And if you've learnt your product of the roots formula, for a quadratic equation, your roots always multiply to c squared over m squared, the coefficient of the constant divided sorry, not the coefficient, the constant term, divided by the coefficient in front of the x squared term. So we've got c squared over m squared is equal to k squared for this particular problem. So that's a condition that holds for these x values of a and b to basically form a right angle triangle with the origin. Okay. Now what that tells us is that c is equal to plus or minus mk. You need to realize that c has to be actually the negative. Only the negative works. Okay, remember that c in a line y equals mx plus c is your y-axis intercept. Now if the slope of the line is positive, the k value will be positive because the parabola is opening up to the right. And your y-intercept of the line is clearly a negative number, so negative mk works. You can actually make the diagram so that the line goes the other direction. Okay, there's nothing stopping you having the point A here and the point B there. In that case, k will also be positive because the parabola is still opening up to the right-hand side. The c value will be positive and the m value is negative, so c will still be equal to negative mk. And then lastly, this is the beauty of this method. How do we find the the x-axis intercept? Well, of course, we take our equation mx plus c, but our c value is now negative mk, and we make it y equals 0. When y is equal to 0, we get mx is equal to mk, x is equal to k. How cool is that? Okay, so that method there was definitely a lot nicer algebraically, but you needed to get that relationship between the x values of the 2 points and then realize it connects to the product of roots for a quadratic equation. See you in the next video.